So now let us welcome our fourth speaker, Professor Danjie. Professor Zhu is currently an associate professor at Jiangsu University of Science and Technology. She received her PhD from University of Guelph in 2022. From 2022 to 2024, she worked as a postdoc researcher at Dalhousie University in Canada. She joined the Jiangsu University of Science and Technology in 2025. Her research interests include path planning and control of underwater robots, cooperative control of multiple AUVs and surface vehicles. Today, she will present a talk, Adaptive Safety, Critical Navigation of AUVs in Complex Marine Environment. Please join me in welcoming Professor Zhu.
Can everyone see my screen
Yes, we can see your screen.
and also hear my voice, right?
Yeah, yeah.
Good morning, afternoon, and evening for everyone. So this is greetings from China. And before the presentation, I have to say sorry that recently I just caught a cold, so apologize for any possible unclear in my oral presentation in the following section. My name is Danjie. I'm now at Jiangsu University of Science and Technology as an associate professor for the second year. So today I am very honored to present our work on the topic of adaptive safety critical control for AUVs in complex fluid environments. So as we all know, the development of autonomous underwater vehicles, abbreviated as AUV, in real world ocean missions faces two invisible challenges. So first is the fluid disturbances, and the other one is the intrinsic actuator lag. While the traditional planning methods focus on finding the shortest path, they often fail to guarantee physical safety when the vehicle is pushed by strong currents or hindered by the response delays. So beginning from the concept of safety, while we have already established the bridge between safety and set invariance, following the work done by Dr. Aaron in 2019. So actually in their paper, they raised the conclusion that the safety is equivalent to the forward invariance of a safety set, which always written as a C. So this means if for our work, this means if the AUV starts inside the safe region, the control law ensures it never leaves it, while the liveness is often viewed through the lens of stability, like reaching an equilibrium point. Safety is about the boundary. The relationship is like lifeless provides a desired behavior, while the safety acts as a god, acts as a god. So in the CBF framework, the control barrier function framework raised by Aaron in 2019, this paper, actually they don't just hope the robot stays safe. We also prove that the safety set is forward invariant, making safety an intrinsic property of a closed loop system. So to prove invariance, we look back at the Nagumo's theorem. The theorem states that for a set to be invariant, the system's flow, the velocity vector at the boundary must point into the set or be tangent to it. So in the context of AUVs, this means that as the vehicle approaches an obstacle, the control input must be chosen such that the derivative of the safety function Hx, the derivative of the safety function Hx remains inactive. This is a safety critical condition. So that means if the vehicle is moving toward a collision, the control barrier function, the CBF, will generate a counteracting command to push the state trajectory away from the boundary, effectively rendering the obstacle occupied space unreachable. This is a dynamic graph showing how the CBF function works, which proves that if the vehicle is moving toward a collision, and the CBF function will be inspired. So it will generate a counteracting comma to push the state trajectory away from the boundary and effectively rendering the obstacle occupied space unreachable. So in practical control synthesis, we use two types of Lyapunov-like functions. The control Lyapunov function, CLF, is a carrot, pulling the AUV toward its goal to satisfy liveness, while the control barrier function, CBF, is a fence, pushing the AUV away from danger to satisfy safety. So moving from the general theory to the AUV navigation, we introduce this path planning methods, which is a navigation based on the mechanism based on the fluid mechanics. It's unlike artificial potential fields, APF, though it's kind of similar to it, which often suffer from the local minimum. I mean, the APF method is often suffered from the local minimum problem. The navigation based on the fluid mechanics, it mimics the physics of fluid flow. It treats the obstacle as solid bodies in a stream. So the AUV follows the streamlines that naturally wrap around the obstacles. Each starting point generates a unique non-crossing streamline, providing a smooth and globally convergent path towards the goal. So this also provides the liveness component of the navigation, a high quality and geometrically safe path that avoids common disadvantages of the traditional navigation methods. So for these methods, navigation based on fluid mechanics, we have a typical one, which is called Interfered Fluid Dynamical System, IFDS. Its mechanism is kind of shown on this slide. So we have the original flow field at the very beginning. The goal is regarded as a sync point. And at every position on this map, there's a streamline forced directly straight into this goal point, which is kind of similar to APF method. But the difference is when there's obstacles, the original flow field will be interfered by the shape and position of this obstacle and creates an optimal planning path accordingly. So this is formulas and how the interference is created based on the shape and position of these obstacles. So not only the sphere obstacles, but also for like cylinder and rectangular obstacles, it can also works as well. So for our work, we consider about the limitation of the IFDS, the navigation based on fluid mechanics. The IFDS has a critical flaw in real-world underwater environments. It is actually pure geometry. It assumes the AUVs can follow the streamlines perfectly. However, the AUVs have high inertia and suffer from significant control latency problem. And the control latency here, we use the letter tau to represent the control latency here. So in these cases, the vehicle's momentum might carry through the IFDS boundary, leading to a possible collision. To solve this problem, we propose the method called Streamline Filtered Control Barrier Function, abbreviated as SFCBF. So SFCBF acts as a supervisor that filters the IFDS velocity. It introduces a predictive lag compensations term, which I will just introduce in the next slide, which anticipates AUV's future position based on its latency and adjusts the steering. So this is the preliminary simulation results in 2D cases. So this is a predictive compensation for the control latency we designed in the embedded CBF function. And so here the tau is the control latency. And this parameter, the projection of the relative velocity, which is the projection of the relative velocity onto the normal vector of the obstacle. So relative velocity here means the difference between the obstacle's velocity the velocity of the dynamic obstacles and the vehicle's velocity. So based on this predictive compensation for the control latency, we can finally derive the simulation results here. So under the 2D cases, here we have two dynamic obstacles. The first one, the obstacle one, is the one we assume it is heavier and moving in a straight line action. So from the position at 4, 6 to kind of the position at 6, 1. So here you can see the methods, especially our proposed methods SFCBF, it successfully avoids the dynamic obstacles, while the IFDS it drops under the safety buffer. And the conventional APF, it just falls into the bump zone, which means it bumped with the first obstacle. And the second obstacle, we assume it is lighter and smaller. That means it might be affected by the ocean currents we design flowing from the top left to the bottom right, and moving in a curvature line. So from the position of at 8, 8 to the position at the top right. So here for the second obstacle, our proposed method SFCBF also avoid the collision and compared to the conventional methods such as the standard IFDS APF, our proposed methods shows a better performance, which never approaches the safety buffer or even approaching to the bump zone. So this is the cases when the control latency is around 0.2 seconds. And this is a comparison while the control latency is increasing from 0.1 to around 1.6. And you can see the comparison between our proposed methods SFCBF and with the standard CBF that does not consider the lag compensation. So here, with the increment of the control latency, the standard CBF creates is gradually approaching to the safety buffer, which means it is getting more dangerous for creating the collision, while our proposed methods still always sustain around the minute distance at around 1, which means it satisfies the safety whenever the control latency change. So here is the 3D cases. Oh, we actually have the animation, but I don't know why this is not working on the slide. So for the 3D cases, we have these sphere obstacles. All the three sphere obstacles are moving dynamic obstacles, while the fourth obstacle is a static obstacle. So here we have the control latency at around 0.8 second. And you can see that compared with the standard IFDS, that does not consider the safety, it directly falls into the bump zone while encountering with the first obstacle. And our proposed method, SFCBF, always sustain above our safety buffer from the beginning to the end. So all these prove the superiority of our proposed method. And for the feature plan, we plan to combine maybe the reinforcement learning to kind of realize the dynamic parameter self-tuning, like to adaptively optimize the decay rate alpha in the control barrier function and the lag compensation gain in our compensation, in our predict compensation designed for the control latency to use reinforcement learning to kind of dynamically tune this up. One might be implement a reward function that optimizes soft objectives, such as the energy efficiency and mission time. As you can see in the previous results, although our proposed methods satisfy the safety requirement, it somehow shows like a less efficient rule as it creates like longer distance other than other methods. So so we might include a reward function that to find a balance between efficiency and also the safety. The third one might implement a hierarchical navigation architecture. For example, use a high-level global planner, the A plus or RT to generate waypoints that guide the vehicle out of concave traps. That is all for my presentation today. Thank you for your attention, and it's welcome to contact me at Jiangsu University of Science and Technology. Again, greetings from Zhenjiang. Thank you.